In this video, we solve a few problems involving exponential type indeterminate form, so 1 to the infinity or 0 to the 0. This is an example. As x approaches infinity, 1 over x approaches 0. So this is 1 plus something approaching 0. So the base of this sort of exponential type form is approaching 1, while the exponent is approaching infinity. You might say, well, isn't that definitely going to be 1? Well, if the base approaches 1 faster than the exponent approaches infinity, I might expect that that function or that value would equal 1. But if this goes to infinity faster than this goes to 1, well, if our number is greater than 1 as that happens, the value of the limit might be infinity. Or if our number is sort of less than 1 as that happens, the value might be 0 because we're taking a fraction and raising it to a very, very large power. So you could get 0, you could get infinity, you could get a finite number, and it really just depends. The way that we handle this is just using the log property that the log of a to the n is n times natural log of a. So, and we're going to use that fact and this expression. We're going to take the log of both sides. We'll let y equal the limit that we're looking for. And then we'll take the log of both sides. And this log of the limit is actually equal to the limit of the log, provided that this limiting value is in the domain of the natural log function. So we can pull that logarithm inside. And we say, okay, I've got log of some function to a power, so I can bring that power down just using this property of logarithms. And so I have x times natural log of 1 plus 1 over x. Now I'm thinking of this as a new problem. So I'm saying to myself, okay, this is a 1 to the infinity indeterminate form. What about this one? Is this something that I can just evaluate? Well, x approaches infinity as x approaches infinity, obviously. And then as x goes to infinity, 1 over x goes to 0. So we have natural log of 1, but natural log of 1 is 0. So this is an infinity times 0 indeterminate form. So you might say, okay, how do I handle that? Again, multiplying by something is the same as dividing by the reciprocal of that something. So instead of multiplying by x, I'll rewrite this expression as natural log of 1 plus 1 over x divided by 1 over x. So I've got this divided by this, and we're taking the limit as x goes to infinity of that. So now as x goes to infinity, I've got natural log of 1 in the numerator, which is approaching 0. And as x goes to infinity, 1 over x approaches 0. So we've got a 0 over 0 indeterminate form. All right. Now that we have a 0 over 0 indeterminate form, we can use L'Hopital's rule. We have the derivative of the numerator divided by the derivative of the denominator. And in the numerator, we've got to apply the chain rule. We've got this 1 plus 1 over x function inside the log function. The derivative of a logarithm is 1 divided by the inside function times the derivative of the inside. And then we're dividing by the derivative of 1 over x. The derivative of 1 over x and the derivative of 1 plus 1 over x are the same, so those reduce. And now we just have the limit as x goes to infinity of 1 divided by 1 over x. And 1 over x goes to 0. So we end up with a 1. Say, are we done yet? No. Natural log of y is 1, and y was actually our limit. So we have to exponentiate both sides in order to get y by itself. So if we have natural log of y equals 1, and we're trying to figure out what y is, we exponentiate, and we have y equals e. Or in other words, the limit as x approaches infinity of 1 plus 1 over x raised to the x equals e. And that's our exponential base, or our natural exponential base. So question is, in this this world where this function is, or this function is approaching one, this function is approaching infinity, which one sort of gets there faster? Well, they're sort of approaching at the same rate in some sense. So we end up with a finite number, and that finite number is about 2.72-ish. So we've got that. That is E. Now let's see if we can't look at another exponential type indeterminate form. Let's take the limit as x goes to 0 of cosine of x raised to the, let's say x squared. I just made that up, so I don't actually know if this is going to work. So as x approaches 0, the base approaches 1. And as x approaches 0, that exponent approaches 0. So I have 1 raised to the 0. So I think that the value of the limit should just be 1, right? Because 1 to the 0 is 1. I'm not sure if that works. So I think I'm going to let y equal that limit. And then we'll take the log of both sides again. And I've got log of something raised to a power. So we can bring that power out front. All right, now as x approaches 0, cosine of x is approaching 1. And cosine of x is just like a small number to the, cosine of x is approaching 1, and natural log of 1 is 0. So this is approaching 0, and then this is approaching 0. So we don't actually have an indeterminate form here. We've got natural log, or the limit as x approaches 0 of this function is 0 times 0, which is 0. So you'd say, okay, well, what does that mean for y? Well, y has to be e to the 0 then. Y must be equal to 1, because the natural log of y is 0. So in other words, the limit as x approaches 0 of cosine of x raised to the x squared equals 1. Now I'm still not sure if this 1 raised to the 0 is an indeterminate form. But it might not. It might be indeterminate, but it might not. So just to play it safe, I took the log of both sides so that I could evaluate the limit of the product, and then use, it's basically the same technique here. There's nothing wrong with using this technique in this case. It's just something that we could do so that it would allow us to find the limit. So I applied that here, even though this might not even be an indeterminate form. Trying to think of one where we've got a 0 to the 0. Let's take the limit. Take the limit as x approaches 1 from the right of natural log of x raised to the x minus 1. This is actually from the textbook. As x approaches 1, natural log of the base approaches natural log of 1, which is 0. And of course, 1 minus 1 is 0. So this is a 0 to the 0 indeterminate form. You might think that the answer is either 1 or 0, but we don't really know. So we'll just set y equal to that limit, take the log of both sides, and then we'll use exponent properties on the left.